Friends, welcome to my YouTube channel. Dhanesh here. In this video, I am going to do an implementation for transfer learning. This is the second video on transfer learning. If you want, you can watch the previous video as well. Here, I am giving an idea about the math behind transfer learning as well. Let's start. No need to waste time. Let's start. I will close this. Yeah, fine. So in this video, as I told, this is if you want more theory related to transfer learning, you can watch the previous video. I will give the description in the I will give the link in the description as well. You can watch that video as well. Let's start with the implementation part. Before that, I am giving a small introduction to transfer learning. It's an important concept in machine learning and artificial intelligence. Transfer learning is used in deep learning, NLP, and computer vision. See, the concept is an example from a human perspective. If you know how to ride a bike, then you can use that knowledge when learning the four-wheelers driving. So the same concept, we can use it in machine learning models as well. This is the math of transfer learning. The domain D is equal to psi of P of X. Here X is equal to X1, X2, Xn, and Xi is element of this symbol. You may be familiar. This is element of. This is the symbol. Element of psi. So what is D here? D is the domain. And psi is the feature space. Px is the marginal probability. X is the sample data point. Simple. Now this is the complete idea of transfer learning. T is the task. Then Y is the label space. And eta is the cost function. This tuple will completely describe the math behind transfer learning. So this can be rewritten as the cost function or the objective function or loss function can be written as the conditional probability of y with respect to x. That is the concept. So the softwares using here are TensorFlow, Python, and I'm using the Google Collab. It's an interesting tool to get the extra memory and all. You are in the previous videos also I have mentioned about that. I'm having the spider as well. See, this is from Anaconda. You will get it. I have the code here, but I have already run the program in Google Collab. I will show you. This is the program. See, it takes some time to train the model and all. So I have already trained it, and the output is here. Anyway, I will try to run it once again so that you will get it. Okay, so this is the Google Collab. If you I have in the previous videos as well I talked about Google Collab. Here, how do you connect? See, how you get this window means you can go to this URL collab.research.google.com. that's all. Then after that you will get a see. If you go to this window, you will, for example, if you are typing here Google Collab, you are getting me. Then you are collab.research.google.com. if you're the new notebook, then you will get the Google Collab. See, now it will be opened. So this is the way you are getting the Google Collab. So this cell, you will click on the play button. You can run that cell, that code. You can run it. See, the things you need to understand here. You will connect the runtime. See, you will change runtime. See, it's already I have done. It is, you need to select the GPU and you need to save it. That's all. So I have already done it, and you need to here you have to click on connect. Then you will get this a green mark, you will get it. That's all. We will be having a 13.5 GB of RAM is available here, so it's easy to train the models by using this tool. It's a very interesting tool. Sometimes if we need, it will give extra memory up to 25 GB RAM. Sometimes it may be busy as well, not always. See, let me here, I am in this, see, as I discussed transfer learning, we are using the capacities of one model, and we are reuse. It's like a reusability, right? Even in object oriented programming, you have the reusability. Even in Python, we can reuse the code. See, here also we are the reusing. That's what I, as I told you, the example of even humans, if you know math, you can, or statistics, you can use it and reuse it in your data science. That's the same thing. So I am importing the numpy and the tensorflow. These it's imported. After that, I am just you have to click, then it will run. That's all. It's a simple process. See, it's already downloaded. It's still now it's again downloading and preparing the data set. That's what it's doing now. It is preparing the data set. We are using the data set we are using here is the TensorFlow data sets. You can use the TensorFlow data sets as TFDS, and you can get that data set. This is the piece of code, simple piece of code. We will use it to get it. Fine. I think it will take some time. Let's wait. Anyway, I am not planning to train the model, because for training it will take a lot of time. I have already trained it and the output is there in the Google Collab. I will explain that. And after that, when you can print the row underscore train and the row underscore test, then you will get this output. This is the output, you will get it here. You understood? This is the output, you will get it here. After printing the training, row underscore train and row underscore test. Now what we are doing in the next piece of code, it is show the first two images and labels from the training set. We are using the metadata.features, and we are using the for loop here, and we are just showing the first two images and labels from the training set. You can see it here. This is the first two images. It's printed. Now in the next, we use the tf.image. This is the tf.image module to format the images for the task, resize the images to a fixed input size, and rescale the input channels to range of -1 to 1. For that, we are using this function of format example image comma label, and we are using this function to do it. That's what we do it in this function. After that, what I am trying to do is apply this function to each items in the data set using the map method. I am using the map method to apply this to each data set. That's what we have done in the next piece of code. Now we are shuffling the shuffle and batch the data by using, we have the shuffle dot underscore buffer underscore size is equal to 1000, and we are shuffling and batch and shuffle and batch the data by using this piece of code. Now what we see, if you want to, let me I'll see whether the data set is downloaded. Yeah, it's done. If you some of the piece of codes, we can run it. See, this one I am running it again. You can see it here. See, it's executing the training, and that part I am not doing because it will take a lot of time. I have already the output with me here. I am just running it will show the first two images as I explained. here this piece of code also we can run it. This is for resize the image to a fixed input size. That's it's working, you can see here. Now after that, applying this function to each items in the data set by using this code to the all the maps we are using that. Now we shuffle and batch the data by using this piece of code. If you run it, you can see here, you can see the output. See tensor shape, it is 32, 160, 163. That's what we get it. After that, we instantiate a MobileNet v2 model preloaded with weights trained on ImageNet by specifying the include underscore top is equal to false argument. You load a network that doesn't include the classification layers at the top, which is ideal for the feature extraction. That's what we are doing in this part. We can run it. It is executing fine. We are using the tf.keras applications mobilenet v2, and it is again downloading the data set. Downloading the data from this, storage.googleapis.com, TensorFlow, Keras, this. So from here it's downloading. I think it's so in this piece of code, what I am trying to do here is the feature extractor converts each 160 into 160 into 3 image into a 5 into 5280 block of features, so that it does to the example batch of image. So it would be, that's what we are doing. It is converting 160 into 3 into 5 into 5 into 1280 block of features. That's what we are doing here. If you run it, let me see here. Yeah, you will get this. Yeah, 3255,280. See, 5 cross 5 into 5 into 1280. We got it. That's what we have done. Now what we are doing is we will freeze the convolutional base created from the previous step to use a feature extractor. Additionally, you add a classifier on top of it and train the top level classifier. That's what we are going to train it. So let's run it. It will, I think, let me see if it's taking more time. I think it's printed. See all the details, it's printed. You can see here. It is total parameters it's given, trainable parameters, non-trainable parameters. It's shown here. Everything it's showing here. Now to generate predictions from the block of features, average over the spatial 5x5 spatial locations using a tf.keras layers global average pooling 2D layer to convert the features to a single 1280 element vector per image. That's what we do it in the next piece of code. That's what we do it. For that, see, if you run this piece of code, what you can see here is it will, you will get it. It will see 32, 1280. That's what we can do it here. Here you can get it. Now we apply the tf.keras dense layer to convert these features into a single prediction per image. You don't need an activation function here because the prediction will be treated as a logit or a raw prediction value. Positive numbers predicts class 1 and negative numbers predicts class 0. When you run this, you will get it is 32 comma 1. You are getting it. Now we will compile the model before training it. Since there are two classes, use a binary lows with from underscore log IDs equal to true, since the model provides a linear output. See here, this is the we will get the model.summary. When you run it, you can see it here, model.summary. Okay, this is the one. See, I am going to run it. See, you have got the all details, the output shape, param, total parameters, trainable params, non-trainable params, all these. The 2.5 m parameters in MobileNet are frozen, but there are 1.2k trainable parameters in the dense layer. These are divided between two TF, variable objects, and the weights and the biases. See, if you see the length of the model trainable variables, you can see it as 2. You can see it here. Now I am going to the initial epochs, I am taking it as 10, and the validation steps I am taking it as 20, and I am the lows model dot evaluate. We are going to train the model, but this will take a little time, so I'm not going to execute it. If we have got the initial lows as 0.84 and initial accuracy as 0.48, we got it. So if we train the if I execute it, it will take a lot of time. So I have done it previously, and you can you can see it here. So that's what here. Now what I'm going to do is see here I have given the history. So this is a history equal to model dot fit. Now you can see it here. Model dot fit train underscore batches epochs and validation underscore data equal to validation underscore batches, and when I execute it will it will train this model, and after that I am doing the base underscore model trainable equal to true. I'm just printing the number of layers in the base model is 155 as we discussed. Then here we are fine tuning from this layer onwards. We are doing a fine tuning here. It is 100. Here again we are compiling and we are getting the summary. I'm not executing this piece of code. I have already done it because it will take a lot of time. So here we have the total params and the trainable params it's got, and the length here we got it as 58. After that, the history ACC is equal to history accuracy, and the value underscore ACC, that is here we have the history, and I am trying to loss also we have value underscore loss. I am trying to plot all the variations like the training accuracy, validation accuracy, all these things I am trying to plot. I am going to cross entropy. So this is the plot we will get it when we run this piece of code. The training and validation accuracy is this. You can see here the training accuracy is in the blue color and the validation accuracy is also there. It's the plot we got it. It's now you have the cross entropy and the epoch. That variation is also got for training loss, and the validation loss we got this. After that I have taken this fine underscore tune underscore epochs is equal to 10, and the total epochs I am defining this initial epochs plus fine tune epochs, and I am getting the history underscore fine. Again I am trying to train the model. It's it will take some time. I have already done it. If I have stopped it and I have already got the data. See now what we are doing is let's take a look at the learning curves of the training and validation accuracy loss and the fine tuning the last few layers of the model at V2 base model and training the classifier on top of it. That's what we are you need to understand. The validation loss is much higher than the training loss, so you may get some overfitting. You may also get some overfitting, and the new training set is relatively small and similar to the original MobileNet V2 datasets. After the tuning model nearly reaches 98% accuracy, see, you need to understand. I have already run this piece of code because you can see here the accuracy, it's almost 98 percentage accuracy we got it. You can even in the plot you can see the training and validation accuracy and the training and the validation loss. Here we have the training accuracy, the validation accuracy, and the start fine tuning. All these things we have given here. So we use now, you can see this graph. After that, we using a pre-trained model of, this is the summary, we can get it. Using a pre-trained model for feature extraction when working with a small data set, it's a common practice to take advantage of features learning by a model trained on a larger data set in the same domain. This is done by instantiating a pre-trained model and adding a fully connected classifier on top. The pre-trained model is frozen and only the weights of the classifier get updated during training. In this case, the convolutional base extracted all the features associated with each image, and you just trained a classifier that determines the image class when that set of extracted features. Fine-tuning a pre-trained model to further improve performance, one might want to repurpose the top-level layers of the pre-trained models to the new dataset via fine-tuning. In this case, you tuned your weight such that your model learned high-level features specific to the dataset. This technique is usually recommended when training the dataset is large and very similar to the original dataset that is pre-trained model was trained on. So this is what you need to understand about the implementation part of the transfer learning. So that's all. Thanks for watching. Please like, share and subscribe. Thanks a lot.